So good evening from Tokyo. So shall we start the ESP training session in the third ESP Asia Conference? So welcome to this session. So my name is Hiromu Okazawa and the professor of Tokyo University of Agriculture. And so in this session, so I'm a chair. Yeah, nice to meet you. So sorry. So before starting the training, so please change your Zoom ID to your name and so affiliation like this. So for example, so name and so yeah. Please change your ID. So oh, sorry. So this is the time schedule of this training session. So first is, so I will give some information about this training session. Then, so there are 4 presenters in the training. So first presenter is so Professor Ferdinand Villa from BC3. So second presenter is so Stefano Balbi from BC3. Third presenter is so Kiichiro Hayashi from Nagoya University. Then, so last presenter is so Yuri Yamasaki from Tokyo University of Agriculture. So after completing also presentation, so we will have a question and discussion session. Okay. So first of all, so I will give some information about this training by using the PPT file. So can you see the aims of the slide? Okay. So in this training, so yeah, this is the aims of this training. So first is the training class of ARIES. So we call so artificial intelligence for environment and sustainability. So we'll give the participants. So first is so how the ARIES web system works for data and model integration through the semantic web by providing a live demo showing. So second one is so how its web interface. So we call so K Explorer and so ARIES for SIA Explorer work as well as showing how customized model work under the K modeler. So the training class will be conducted by the ARIES team by so K Lab Japan member. So I'm a member of so K Lab Japan. So after attending this class, so the participant will gain enough knowledge and skills to use the ARIES existing data and model with K Explorer. So finally, so they will understand, so all participants will understand the future possibility for the applications of customized model. So I guess so almost participants so already got the manual, so how to install K-Lab for your PC. So if you don't have a manual, so please get this manual on the ESP Asia training so website. So it's a PDF file. Then so please install the K-Lab system on your PC. So next, so I will talk about the goal of this training. So introduce so ARIES so that participants become so familiar with the modeling framework. So introduce so K Explorer and so ARIES SIA so that participants can feature Explorer and use the models by themselves during and so after the masterclass. So introduce the example for making ecosystem service modeling and other by K modeler. Then so provide a venue for future collaboration on ecosystem service modeling. Those contents will be a goal of this training session. So once again, so I will show you the today's schedule. So yeah, so I just complete my agenda for the training. So second, so okay, sorry. So shall we move on to the first speaker? So first speaker is Professor Ferdinand Villa from Basque Center for Climate Change, so we call BC3. So yeah, he's a leader of ARIES project. So he will give us about the overall of ARIES project firstly. So please get start your presentation, Vila. Okay.
With pleasure. Thank you very much. And it's very nice to be there in Nagasaki, although virtually. That's something that we hope to fix one day. So I will need Okazawa Sensei to stop sharing his screen so I can share mine. We can only share one at a time.
Please.
Perfect. Thank you so much. So give me 1 second. The options are many here. So the entire screen, share. Okay, I trust that you are able to see my screen at the moment. So I will not go through any presentation except for this one slide, which is meant to give you an idea of how the ARIES system works. I apologize for the messy slide. It's meant to be shown piece by piece. So that's what I need to do. Slideshow and start from current slide, like this. So as you can see, these are the different components of the KLab ecosystem, which is the infrastructure that runs the ARIES platform. And I will show directly or indirectly all of these pieces today, but not explicitly. So I thought it would be useful for you to understand how the system is put together. So we have been hearing about installing the KLab environment on your computer, but it's not something you necessarily have to do. As you will see in your notes, the KLab system can be used from the web through a web browser without installing absolutely anything. But we are going to see today both the configuration for a regular user, which is entirely fine through the web, and the configuration for a modeler, which requires you to have an interface and a local engine so that your machine can do the calculation and you are free to load and unload the models from your own instance of the system. So when you use KLab, you are using an engine, which is the server, the machine that actually builds and computes the models. And this engine connects to a network, which is a large network composed by many different nodes. And those nodes is where the knowledge is located. So both the semantic part of the knowledge and the meaning of things and the models themselves and the data, they are all organized and loaded through nodes that are distributed all over the network. So that's why we talk about building a semantic web of information. There is no need for data or models to be on a user's machine in order for the system to be used, but it is possible to use the system in a modular configuration so that you can actually add your pieces, and when you're finished, if you have the privileges, you can upload those pieces to a node or your own node if you are so inclined, so that they can be shared with others. And this distributed nature of the platform is what makes it powerful. No modeler by themselves will ever build things that are as useful as a community of modelers working together using an infrastructure that can connect the knowledge coming from different parts. And that's why we have built this system. There is also a hub, which is a one server. Typically, we have just one at the moment, which is the one that organizes the traffic and gets users authenticated. So that's why that's the first instruction in your instructions is to go to the hub. You have the link for that and get yourself registered, get a certificate, which is basically our key to enter the system, which just tells us who you are. You don't have to pay for anything. And through the hub, you will be able to access all the engines, all the nodes, etc. And then there are two parts that stand on the desktop of the user. One is the modeler, which is an interface through which we build and add new models and new data to the system. And we will show a little bit of that today. And the K Explorer, which is the easier part, which is basically the web interface that you can connect to. And it is the front end for users who want to use the system. And whoever uses the K Explorer can be a modeler, an expert as much as they need, but they can also be non-experts. And the system is designed for non-expert users to be able to do all the functions that the system allows. So we have different sets of expertises in here. If you want to work at the engine level, you have to be a modeler. If you want to work at the node level, you need to know about networks and things like that. But there is at least one entry point for all levels of expertise and for all kinds of usage. So I'll now switch to my browser. And as you see, I've just put up a map. This is basically what you see when you connect without loading an application in the system. So because we are virtually in Nagasaki, let's move around Nagasaki here. I'm using OpenStreetMaps as the base layer. We have a choice of those, but I like OpenStreetMaps because it's respectful of local identities. So I need to know where Nagasaki is because I cannot read Japanese, at least not very well. But but you can obviously go in any place in the world, and you can actually tell the system to locate a particular part of the world by name. For example, if I say Nagasaki, it would probably give me the choice between Nagasaki City, the port, the bay, or the prefecture. Prefecture is a little bit more regional in scale, which is the scale we normally work at. So maybe we can choose that. And once we have a choice made in the system somewhere, you can basically ask the system to make an observation. And the crux of the semantic web modeling is that you don't actually call or invoke a model. What you do is to invoke a concept, and you basically ask the system in near natural language what it is that you want to observe. And I maybe want to observe something very simple, like, I don't know, the slope which is the inclination of the above water terrain. So you see that there is a knowledge base here, and there are different things that start with SLO, which I wrote. A slope as an object, you see the S here, it's for subject, could be the actual region where the land is sloping. So basically the side of a hill, for example. But the slope as a quality, which is something you can measure, which is a green, it's a Q, then that will be basically producing you in a spatial context. It will produce a map of the inclination with the angle of the terrain in each location. And look, we can try to just observe that. If we make our choices, green means it's a quality. I click return, and the system gets set up for making the observation after setting the context to the Nagasaki prefecture here. And this is very quick because it's a very simple observation. It basically locates a data set and you don't need to do much else. And in other situations, the system may decide to locate a data set of elevation if it doesn't have a data set for slope, and then compute the slope using morphological calculations. That would be longer. Fortunately, we do have a data set for the global world at the resolution we are interested in. So if I just click on this, you will see that the system will give me the slope in each point, and I can click and see the slope in degrees. I could ask for it in radians, for example. It would just be a matter of adding that part, the unit, to my question. That's basically the way the system works. But obviously, it's much more interesting for you to look at things that are more complex than a single data set. So when you connect to the system, you typically have a number of groups. Then you will see that when you connect for the first time, there will be a choice of groups. Those groups are basically meant to tell the system what you're interested in, so that the system can give you a number of choices that you can start from. And if you press the spacebar over here, instead of typing, you will get a number of choices that will change in time according to what you choose, like in Google, more or less. It tries to learn your preferences, but at the moment you will mostly see this kind of things if you are in the ARIES group, which is obviously about sustainability and ecosystem services and things like that. So you can make any choice in here. For example, net value pollination. Net value pollination is obviously a much more complicated concept than slope, so it will require many more calculations in order to be computed. So if I click on here, the system will try to find the best way for this context to compute the slope. And you see that many observations are coming in already. While if I show you this part of the view, we just click on this symbol, this is what we call the data flow, which is basically the model that the system has built in order to observe that particular concept, the net value of pollination. So in order to do that, it needs data observations like land cover and probability of flowering and a number of other things. I'm not going through the explanation of how this works, but you can see that as calculations move forward, these different boxes get highlighted, and it means that at that particular moment, that particular element of the flowchart is being computed. And this is a fairly fast calculation. So I will first show you the end result, which is the net value of pollination here. So if I click it, I get this map, which tells you in red, it tells you the areas where pollination is lacking. So there are crops that need pollination, but there is less suitable environment for pollinators than would be necessary. While you're having it in green here, it means that there is more pollinator habitat than there are crops. It means that there may be no crops at all, or there may be crops, but they are completely okay from the point of view of pollination. And if it's around white, it means that probably the situation is in balance over there. It's one of the many things you can ask the system. Obviously, you have all the choices, but it's one of the maps. And you can, as you see, it's being computed quite quickly because it's much less simple than just getting a data set, but it's still a relatively simple model. The system is capable of dynamic modeling, hydrological modeling, a lot of things that actually may require a whole lot of time to compute. And as you see here, this is a report that gets built automatically because the system is semantically driven, so it knows about what it's doing. It knows by name and by concept what it is computing. So it's also able to write a report in more or less the way that a human would do, obviously not particularly creative, but still a satisfactory report if you need to know what has happened in your simulation. And it is very important in a system like this to have complete transparency about the calculations that have been undertaken, because in each situation, those calculations could be different. Because the system is set up so that in each context, it will try to resolve your query, your concept, using the model that is most appropriate to this concept. So if you are in a different scale, for example, if you zoom in or out, the system may choose different strategies because it maybe have fine resolution data sets that only cover a particular area, so using different data, but it may also be able to choose a different strategy that is more precise, for example, using individual-based or network-based models instead of using just raster maps. So you will see these things coming up in the future as well, and as more people use the system and they contribute more models, more alternatives will be available. So you have a number of views here, and you can just go through this report in the way you want. It's indexed, so you have figures, you have the net values, you have all the maps with the legends, the lookup tables that have been used, etc. You can also look at the system through different views. If you look at the figures only, for example, or more importantly, this is a very important view, you can look at all the data sets that have been used, and for the sake of transparency, any data set that has been used by the system is available here. It's shown in its coverage. And if the data are public, you also have a link to download them and to go to the original website. By the way, we don't necessarily have to store those data ourselves. Very often, the original providers make them available for us for streaming, like geographical servers, etc. In those cases, the system takes them directly from there. So it works as an integrator and an aggregator of information rather than a depository, a database of information, which is very important for us because the scalability that this gives you makes it possible to actually build a network for knowledge and to operate across it instead of having to replicate information and having to make the user choose between one thing or the other. We don't, you don't choose to use ARIES instead of something else. You use anything you want through ARIES, and that's the main important thing. So that is the very simplest view for using the system, and you can reset your context and move somewhere else or do something else by just clicking that button. And as you see, it's very minimal in this particular configuration. But the ARIES Explorer that you're looking at is also a platform where you can build applications. And one of the applications that we built recently for the United Nations allows you to do natural capital accounting, implementing the SIA standard that was approved in March last year. This year, sorry, I'm still confused time-wise, which makes it possible to build application in a very simple way. So you have a choice of applications here. You will see less than what I'm looking at here, but you'll also be able to enter the applications directly from the network system. So it's possible to choose these without having to enter the Explorer at all. So you don't need to remember this particular user action. And I will show you this because it's the one that people have been mostly talking about recently. I'll make it a little larger. The ARIES for C application is, as you can see, it's still the Explorer. You still have this, and you still have all of your choices there. But you also have a driven interface where you can choose resolution. You can choose your context by going through administrative regions. For example, if I am at the zoom level, this will be all of Japan, but I can zoom in and maybe get just one prefecture, or for example, try to go around Nagoya here, and this should be Aichi prefecture, and make your calculations in there. It simplifies this, and you can also use other criteria like watersheds, river basins, etc. This may become more articulated in time. Let's stay in Aichi prefecture for the time being, and then you can make a choice of what you know to compute. Now we're talking about the natural capital accounting here, which is a statistician's field, but it has to do with the ecosystem service part. So we are looking at, for example, extent account is the simplest, is the quickest to compute. So I will just click this one. Extent account is basically looking at the ecosystem types in the system, and you may be seeing this these variables being computed, and it will compute the articulation of the ecosystem types according to the IUCN level 2 classification that the United Nations has chosen for this specific purpose. And as you can see here, I have 2012 to 2019, so it's a dynamic model. It's supposed to show me the change between those 2 years, and obviously I can change both the resolution and the temporal arc that I'm looking at, and then give me a comparison of which kinds of ecosystem and the area for each kind of ecosystem available in Aichi prefecture in between those 2 years, so that I can basically tell my government that my forests have been increased this much, but my urban area has increased, or my cropland has decreased, etc., etc. And in addition to this, it's now computing that table. There is a lot of other things like ecosystem condition metrics, accounts for physical assets like crop provisioning that depend on pollination or depend on the ecosystem contribution, carbon storage, regulation of sediment, etc. And we are working to expand this list. All of these are tables, but they are all based on geophysical data. So you see the table here, and this table is something you can export in Excel, you can download, you can do anything you want. And it's basically tell you the extent of each type of ecosystem here at the beginning and at the end, and how much the net change has been. So you can see here that in Aichi prefecture, between those 5 years, cropland has become less, has lost 70 square kilometers in cropland, and other will have been gained. For example, typically the artificial urban ecosystems usually increase. Indeed, we have gained just about the same amount in artificial. So basically the urban environment has invaded the cropland for this much, not very much, etc. So it's another view, and you can still have all the same views that you had before. You can look at all the lookup tables, etc. The transparency is total in this case, and you can look at the different figures here, and you can actually have the different states of the environment at each point in time. You can go through them, and you can explore the differences at any point in time. And you obviously have the very important list of the data set that were used. So this is just one way to look at the system. Building these applications is not difficult. It is not particularly complicated. This application is like 200 lines of code. So we are trying to train people in building these applications so that any specific bottom line for either governments or NGOs or academia can be easily implemented as a specific interface on top of ARIES, so that users that don't want to know about concepts, semantics, and etc., have a chance to just click buttons and still get results in a very distributed, in a very scalable, and in a very powerful way, because all of these models, when you click the button, will not be simply running one specific model, taking one specific data set, but each time choosing all the different, the best implementation of each model and of each concept that best suit this environment. So because I don't have a lot of time, what I'm going to show you now is how you actually write those models, because this is supposed to be a training. I mean, it's very difficult to do a training in 2 hours and from a remote location. But at least I want to show you all the sides of the system. Many of you will probably be modelers and will be curious about how do I write these things. So I'll switch to the modeler interface, which is also something that's open source and you can download. And I have in front of me the interface that shows you the pollination model that I've just run before in the Nagasaki prefecture. I will make it larger because it's probably very difficult to see. And what I'm looking at now is the source code of the pollination model. So it is just 50 lines, but the reason why it's so short is that it's a semantic system. So a semantic system doesn't need to specify a whole lot of information. It basically needs to just concentrate on the key core algorithms and the key formulas, because all the details about visualizing, running the system, loading data, outputting data, and handling the traversal of space and time that a modeling system requires in order to work are handled outside the system. Basically, all you deal with when you build a model is the core algorithm. So, for example, let's see. It's usually productive to look at this from the top, from the most important concept. So, if you can look at here, model net value of pollination. This is the concept that this model explains. So, as you can see here, it's built not as one single concept, but by combining concept in a logical expression. So, net is an attribute which you can hover your mouse and you can see the definition here. Value of is an operator that takes something that is valuable to you and produces the concept that is the quality that estimates its value. So you can learn this language with this semantic language, more or less the same way you learn English. It's meant to look like English, not because we like English that much, but because English is really the simplest language, because you can put together all of these words and it keeps being grammatical. If it was Japanese or Italian or Spanish, it would be a lot more complicated to do a system like this. So English is kind of the obvious choice because it's so flexible. You can basically rearrange it in any way and it's never wrong. So it was very, very good for as an inspiration for the semantic language. By the way, this language is called KIM, K.IM, which is knowledge integrated modeling, but KIM is a good word in a lot of languages, so we call it KIM. The model, as you see, the top end model is very, very short. So model this concept, observing this other concept, normalize the ratio of pollinated yield to yield. It's a little complicated to write. It takes a little practice, but basically this means that you want the ratio of the yield, the agricultural yield, which is dependent on pollination, to the total yield. So you have, after 2, there is no attribute here. So you take the entirety of the yield, and then you want the ratio of these two, and then you want to normalize that between 0 and 1. And by just mentioning that you want it normalized, the system knows what normalization means, because there is another model somewhere that says model normalized of quality by using this function, by using this algorithm, which basically turns it into a quantity between 0 and 1. So you can build all these pieces independently, and the person who has built the normalization model doesn't need to know anything about the use you will make of it, because the concept of normalization is the same, it doesn't change. And that's the spirit for everything else. So when you write something like this, it means it tells the system, take this concept from the best source that you have for it. So the ratio of pollinated yield to yield, there will happen to be one model right here, so that this file, which is, we call that namespace, is self-consistent. But if there was a better model for that coming from some other researcher in some other part of the world, maybe just for the specific region you're in, the system will choose the best model instead of the default one. You give it enough information to work, but you basically build the skeleton of your application, of your model. But that skeleton can change according to where you are, and the system is able to make these decisions on its own, and then they will document them completely so that you are sure that that you can always have the best result. So you have two observations here. You need to observe the ratio of pollinated yield to yield, and you give it a name here in order to refer to it in the equation that comes after, and the occurrence of pollinator insect, which is the probability for a pollinator insect to be living in each point of your context. And there will be a model for that right up on top of this. So the occurrence of pollinator insect is written in the same way. You need two more occurrences, which also will refer to other data, and then you use another equation. But this part uses this observation is crucially independent from this. You can test this model independent of this. You may have a data set for this, and it will use the data set. So what you see here is not one model, but it's a suggestion for the system. And in the end, when you ask for net value of pollination, the system will find this model if you have no other model. But you have written another model for the same concept that will compete with your model, and according to the context, it may be chosen according to what is the best situation for the system. If it produces a model that is more detailed, that is using better data, that uses more data that are closer to your resolution or to your time that you have put in your context, that model will be prioritized compared to this one. So basically, when we write a model, we write a bottom line model for a particular concept, and then any user who has a better idea can contribute it, and the machine will make the decision which one needs to be used and which one is best in each situation. So very simply here, and just to conclude, because I have a few more minutes, what you get here is that I make two observations. No matter how, I'm not telling it how, I'm just telling it what, and that's the key for semantic modeling. And then I give a name to each of these two observations, which means that it will produce a number in each point of the context. So this number will be between 0 and 1 in this case because it's normalized, and will also be between 0 and 1 in this case because it's an occurrence, which is a probability of presence, so between 0 and 1. And then this will give you the normalized net value, which may be according to the yield, and the pollination could be negative or positive according to the situation. So this is just an example, and the ARIES system is basically the only database we have is a database of knowledge of this kind. So this was the pollination model. We have, for example, carbon models here. They're a little bit more complicated sometimes. Flood regulation are a lot more complicated. Forest evaluation, sometimes they use machine learning, for example. So we have ways to use dynamic modeling in here. We have ways to use machine learning and Bayesian networks, etc., which was our starting point when ARIES was born. We have much more physically based models, like this sediment model that basically is implementing the Russell equation. As you can see here, it's less than simple to look at, but it's in the end, it's still a few lines. And if you try to build a model like this in Python, for example, you will need to first worry about loading the data from somewhere and then outputting your output somewhere else. And then you will have to loop through the space. So you will need to say that, okay, the space needs to be in this resolution and in this projection. Nothing of this is required here because the system is intelligent, so it will apply this knowledge to whatever context you decide, which is why when you use the Explorer, you have the ability of setting the context the way you want, to setting the resolution the way you want. For example, I can go back here and set my context to something square, to a map, to draw the context myself. I can actually draw the context using using just drawing tools. Takes a while to reset. For example, I could just go in here and decide to draw the context by drawing on this map, or just keep the square that I have, and then change the resolution. I may set 75 meters here. I can just go 300, or I can go up or down. I can change my time, and I can make any observation. At this point, I can just choose to look at net value of pollination again, and the system will get me the value of pollination between those 2 years. So it will make a dynamic model for that. So just to conclude this very coarse exploration of the ARIES system, I will show you also the way we can build the applications, and just so you have an idea of how quick the process can be. So the ARIES 4C application that you just saw with the menus, etc., to do natural capital accounting is in this project here. And no, sorry, not this one, this one. And if you look at the application in here, I'll just show you the code. It is fairly simple. What you do is to create this component and basically write a check button. These are the same words that you see on the interface. And then according to what happens, the check button can be clicked and you can put an action after that. So if you, for example, this is a tree for the forest conditions, you have 2 points here. The column means whatever the user has chosen, feed it into this process, choose this role, disable this, enable that, and the entire application that you saw, public web application, ARIES 4C Explorer, starts here and ends here. Is a total of 300 lines. So for us, it's very important that a person without too much training is able to write a complex application that implements any specific kind of bottom line that you're interested in, so that ARIES in the end, the intelligence, the artificial intelligence in the system is capable of showing you, of connecting you to the knowledge that has been developed by many different people. And you don't have to understand all of that knowledge. You don't have to control all the parts of that in order to write something like this. It is a system that is meant to do and to make the best use and to maximize the value of information coming from different people that don't have to coordinate and don't have to know each other in order for the collective knowledge to grow, which is basically the rationale why we have embarked into this complicated adventure, because it's a very difficult thing to build this system. But at this point, it's starting to produce fruits and to be useful for a lot of different applications, and that's why we are talking to you today. So it's exactly 8:09. So I have just 1 minute to say thank you, and to just leave the floor to Stefano for a more in-depth demonstration of a few of the ARIES models. And obviously, the most important things, you're free to test these things yourselves. You have all the instructions to do that. There's nothing to pay for, so you will be able to do whatever you need and check it out for yourself. Thank you very much for your attention, and we can check back at the question and answer later.
So thank you very much, Professor Ferdinand. So, okay, so unfortunately, so we don't have enough time. So yeah, so shall we move on to the next presenter? So next presenter is Dr. Stefano Barbi from Basque Center for Climate Change. So yeah, so today, so he will give us the 2 demonstrations, so carbon storage and so regulation and pollination. Okay, so please get start your demonstration. So Stefano, please.
Yes. Thank you for having us in this training. So I've been given the task to present actually 3 models or bottom lines, like Ferdinando said, carbon storage, recreation, and pollination. So first of all, I would like to say that if you want, let's say, an article, a reference for what I'm going to explain, is this one. It's an article on Science of the Total Environment. It's called Towards Globally Customizable Ecosystem Services Models. And why globally customizable? Let me give you a little bit of introduction on this. So globally customizable because these models are meant to run in any part of the globe with, let's say, global data and conceptualization already predefined by default, but also globally customizable because we envision user running the same models with local data, for example, or because these models are very modular. So all of these models are meant to give a conceptualization of ecosystem services in terms of supply and demand. Also, the supply side and the demand side, I'm going to explain this later, are broken down into smaller components. Users that can use K-modeler can modify these components, so can substitute the supply part with their own conceptualizations, or the demand part with their own conceptualization. So this is why we talk about globally customizable ecosystem services models. So let's move to K-Explorer, and we will access K-Explorer using the online engine. So you don't need to download anything, but what you need to do is to register as a K-Lab user if you haven't done it yet. So you can go to this address, integratedmodeling.org/modeler with 1L, and register if you haven't registered. Otherwise, if you are registered, you just log in. And for example, here I have some choices, different applications that are available for me as a user. I will use the simplest one for the moment. So K-Explorer. Perfect. So first I will set a spatial context. And I will go to the Aichi prefecture in honor of Professor Hayashi. And basically I started typing with a capital letter. And by doing that, in the search bar, I have access to a data set of spatial objects that I can choose from. So at this moment, the spatial context is set. We are working for the moment in a non-dynamic context, temporal context. So the temporal context is static, and the spatial context is set to the Hayashi prefecture. So by typing the spacebar, I have access to this palette of predefined queries that are available to every user. And so these predefined queries are divided into chapters. One is dedicated to carbon, for example. One is dedicated to pollination. There is something on flood, but we are working more on it. Outdoor recreation is available. Then you have sediment, and then you have some experimental models, including monetary models. In this particular case, I want to go back to what Ferdinando has started showing before. So running the pollination query named net value of pollination. So I just click on it. That makes it available in the search bar, and then I press enter. And this will trigger the calculation. So now the system is retrieving all the information that are needed to compute the final output. And first of all, has constructed the data flow. It's like a flow chart where you have the final output and all the input put together in a flow chart, and now they are related to each other in order to arrive to the final output. As I said, we have a supply part, usually is related to a natural environment, and then we have a demand part that is usually related to human use of nature. The calculation is already finished, so we can go and visualize the output. For example, we can click and visualize the histogram and the legend. As we said, it's a net value that goes from -1 to 1. -1 means, so the red part means there is not enough pollination. The white, so around the 0, means there is enough pollination for the demand. And the green part means there is more pollination than demand. So what is the pollination? So what is pollination? What is demand? Let me explain a little bit the model. I'm using some slides from this website, which are the materials from the school we used to do in Bilbao before COVID. And now we are thinking about different formats for training, but these slides are available, so you can go and check that if you want. springuniversity.bc3research.org/ISU 2019. So the pollination model is largely inspired to this model created by Lonsdorf and colleagues. You can read about this in the article Modeling Pollination Services Across Agricultural Landscapes in Annals of Botany. This article was also let's say, implemented at the European level by the JRC. What we have done was basically to try to generalize it for an implementation at the global level. So the supply concepts that we capture in this model, basically are meant to represent insect activity, so the availability of pollinators, insects in their natural habitat. And these are computed, this is computed by looking at different variables, including flower availability, nesting suitability, the presence of water, but also, let's say, weather variables like temperature and solar radiation. The first three together constitute the landscape suitability, and then the rest altogether makes up the insect activity. Well, what is the demand? Well, definitely the demand is agriculture. So the agriculture that depends on pollination, and that's it basically. So agriculture is the demand for pollination. We can look also at the flow chart in this way. On the left side, the supply, on the right side, the demand. Final output, the net value of pollination. So going back to the Explorer, this is the final output. We can check all the layers that have been retrieved in order to respond to this query. So for example, starting from length cover type, in this particular case, the default data set that is used is the ESA CCI layer. Length cover is here. This is insect activity due to weather. This is flowering suitability. This is nesting suitability. So finally, the pollinator occurrence is this one. So this is the supply side. The demand side, we need to rely on global layers for agriculture. So let's say it's pretty coarse, the default information. So for example, here we can see there is more demand for agriculture in this part. And the final result again is net value of pollination. All of these layers, input and output, can be downloaded by pressing on this arrow here. as a picture or as a TIFF file that you can open in your GIS environment. What am I missing? So we show the data flow. You can click on any of these to have information about it, about the algorithm, putting together the particular box. For example, this is the formula putting together the occurrence of pollinators. So this is one way to look at what was computed. Another way is to go and check the automatic report that was generated. It has the typical structure of an article, from introduction to methods to results given, also with the maps generated. And very importantly, the references, also more information in the appendix. For example, these are the factors of pollination dependency by each crop type, particularly important here. Again, all the figures produced, and also the data set used in the calculations with their own metadata. Well, super important to keep maximum transparency about the calculation that was generated. And also the link to the data website where you can get more information. I was saying, in fact, that the information about agriculture is quite coarse, so it's given at this resolution at the global level. It's very aggregated, so it would be much better if a user can introduce the local data, for example, about crop locations. So this is about pollination. I have pre-computed the calculation on recreation in another computer. So I would like to show you the same things, but let's say this is the final output. So this is the data flow. Again, it's quite complex. You have a conceptualization of supply and of demand. For outdoor recreation, the supply is the natural environment providing outdoor recreation opportunities, and this basically is modeled by looking at the level of anthropization of the environment. So the more anthropization there is in the environment, the less is likely that is attractive for outdoor recreation. And then you have the presence of natural features that usually outdoor recreation requires, like lakes, like mountains, and so on. I will give you more details later. On the demand side, basically is the population wanting to have outdoor recreation. So this is the data flow again. This is the report automatically generated. So this model is inspired to other recreation models that have been used for ecosystem services assessment, such as INVEST and Estimap, very similar in many ways. You have a reclassification of land cover type to basically estimate this level of anthropization that I was mentioning. And you have basically the estimation of distances and features of the environment to related to outdoor recreation, and functions basically aggregating these things together. In particular, the supply and demand, it is put together using a Cobb-Douglas type of function. The report again provides you with all the results, including the anthropization part, so it's called MROB here, the theoretical possibility of having recreation without considering, for example, the accessibility. Then you have the accessibility part, so how easy it is to go and have recreation, but also the population density. And when you put everything together, you produce a map such as this one. Again, the reference is very important here. And going back to the results, you have the three main parts. Let's say the final result value of outdoor recreation again is a number that goes from 0 to 1. This is the histogram. You have the demand part that considers population density and also accessibility of the locations. And then you have the theoretical value, which means the potential for recreation regardless of its accessibility. Interesting, let's say, intermediary inputs are basically the level of anthropization, so the human influence. For example, things that are also considered is the distance to protected areas. In this case, there are 500, more than 500 protected areas. Then you have water bodies, waterways. You see how many features were found in this analysis, almost 20,000. And this is all computed on the fly by doing online queries. Distance to streams, so it's calculated after finding the waterways. Then we have algorithms that look at the presence of mountain peaks, and then the distance to mountain peaks is calculated. Same for coastlines. It's easy to show because it's only made in 2 objects, and then other things. One particularly interesting layer is the travel time, which basically informs about the accessibility of the area in terms of time to reach the location. So going back to the presentation, the outdoor recreation model. This is again the flow chart shown in a different way. To summarize, the main concepts for supply are human influence, and then the features of attractiveness for outdoor recreation, so protected areas, rivers and water bodies, coastline and mountain peaks. And then the demand side is given by distance to human settlements, the travel time, and the population density. What I forgot, I think nothing at this point. I can go back to the K-Explorer online. Okay, maybe one thing I didn't mention is that the time is set, if it's not set dynamically or explicitly, it's set automatically for the year in which we are, so in this case 2021, and that the resolution, the spatial resolution in this case was set automatically, matching, let's say, the optimal resolution for having a decent speed of calculations for the spatial context that was selected. But all these parameters can be modified. Now, to conclude, I would like to go and show you the carbon model, but instead of showing it from the K-Explorer, let's say, user interface, I will show it from the SIA, ARIES for SIA application. So I can, for example, reset the context by pressing this button here. And now to access the ARIES for SIA application, I can go to this and access it from here. And this will load the application. So as Ferdinando was showing, you can set the resolution here, spatial resolution, and the temporal resolution here. Let's make it for the moment. We make it static, so we just take it for 1 year to make the calculation a little bit faster. So let me select again the administrative region, this time using this feature. It's again the Aichi prefecture. And I can basically trigger the carbon model by clicking this checkbox. So this is triggering the calculations required for the carbon model. So the carbon model is the carbon model described so-called carbon model described in this article that I was showing before. So what is this methodology? Well, it's a methodology, basically is a massive lookup table that was approved by the IPCC. It's called the so-called IPCC Tier 1 carbon global carbon model. It looks at different variables like the ecofloristic region, the presence of, sorry about this, and the presence of fire, the burn land, the presence of frontier forest, land cover type, the continental region, and assigns a carbon storage factor based on the combination of these variables. Let's say the reference is this one. If you want to check it out, it's called IPCC Tier 1 Global Biomass Carbon Map for the year 2000. Now, if I go back here, basically the system has already computed everything, and I can, it takes you, because we are in the SIA application, the final output is, the main one is given in terms of basically carbon, carbon storage by ecosystem type. So there was a model first that, that has computed the ecosystem types, and then the carbon model, and then there was a model that was basically aggregating the results of the carbon model by each ecosystem type. So this is the data flow. Again, the same section for data flow accessible through this icon here. Then we can go into the report that has different chapters. Let's say the one for accounting, the main one probably for accounting, the main output for accounting are these tables generated in this section here. So these are the tables giving the output for carbon by ecosystem type. So you have basically the storage by salt marsh, by cropland, by urban industrial ecosystem, temperature woodland, and so on, and the total. This is downloadable in as Excel file, for example. And then you also have all the other sections that we saw before. So the report, automatically generated report, in this case, it's a bit different because it includes more information about the SIA methodology and protocol. And for example, the lookup table that has been used to generate the ecosystem types, and also information about the carbon model itself, with again the ecosystem types map aggregated and the carbon results aggregated by ecosystem. And so on until the references and the appendix. Again, here the report, here is the tables. Here you have all the spatial outputs. Also, they become temporally explicit here when the context, the temporal context is made dynamic. And here all the input data resources used. For example, Uncover was by default the ESA CCI. Then we have information about presence of mountains, temperature, world climate, the global aridity index, again, world climate, elevation, soil organic carbon by ISRIC, continental regions, the FAO ecofloristic zones, and more. So again, let's say the baseline, the base model used is the one described in this article, but then through this application, we make it, let's say, accounting compatible, and we are able to generate automatically the tables that accountants need in order to make natural capital accounting for ecosystem services for their countries. I guess this is more or less what I wanted to say. I have still 5 minutes. I think I touched on most of the things. Maybe another thing to say is that with this application, we are opening the way, let's say, to go beyond the ecosystem services and attack other questions like biodiversity targets and sustainable development goals. So there is the possibility to, let's say, have a preview of indicators related to SDGs, for example, by selecting them here and then loading them into the application. Other things that we have done in this application was to develop models of conditions. In particular, we tackled the problem of conditions, condition of forests, and we need to add more about other ecosystem types. For example, grasslands, they behave very differently from forests in terms of conditions, so other models are needed. But in general, I mean, this is a live ecosystem that is making more data and more models available every week. I mean, as long as we can keep on expanding our community, we believe more information, more knowledge will be made available for the community for free. And we hope to contribute to make a more sustainable planet in this way, basically, by making the best information available to decision makers. Okay, so this is what I wanted to say. I think I will stop sharing my screen here. And if you have questions, I'm very happy to take them.
Okay, thank you very much, Dr. Stefano, for your nice demonstration. Okay, so before moving next presenter, so we will have a question and so Q&A session, very short term. So are there any question or comment for Stefano or so for Ferdinand? Nothing? Okay. No need? Oh, so please show the chat. So thank you very much.
There is a question for data sources availability for China. Yeah, so in general, what we have like around 200 data sets that are made available to public users, and they are global data sets, so they cover China too. So definitely the same data is available for China.
Okay, Nicholas, this is okay. Yeah. Okay. So are there any question or comment? I can accept one more question. Comment or a question, right?
More online trainings. Yes, we are planning to actually make a sort of a self-training course online. I mean, we would love to go back to our school in Bilbao, but COVID has changed the world, and we need to adapt. So I think we will move to more online courses. Yeah, that's the idea.
Yeah, we're also working on producing some self-training materials, self-instruction, which will probably be online sometime next year, maybe the next, I don't know. We have a small team, so it's a lot of work to do these things. And also we will definitely invest in training for more specific applications. For example, with the United Nations, we are thinking about building a training program for Africa, for African governments, etc. And if you have anything specific in mind, we can always discuss it. It's there's many ways you can train for this system. So we are trying to explore every single other way that we haven't tried before, because COVID has changed everything, as we said. So.
Yeah. Thank you very much, Ferdinand, for your good information. Okay, so Okay, so shall we move to the next presentation? It's okay? Okay. So next presenter is, sorry, so I can share the program of today's training. So yeah, so next presenter is Professor Kiichiro Hayashi from Nagoya University. So he is a member of K-Labo Japan. And so yeah, today Sophie will talk about the small hydro estimation, solar panel, air regulation, local carbon stock, and so crop model. Then so Dr. Yuri Yamazaki from Tokyo University of Agriculture, so she will be helped on the maybe so small hydropower estimation. Okay. Hayashi Sensei, please get start your presentation.
Slide.
Yeah.
Okay. Just a moment. Okay. Thank you very much for the introduction, Professor Okazawa. My name is Hayashi from Nagoya University, Japan. My topic is especially focused on the K-modeler application. So the previous one, Professor Mira and Dr. Stefano more focus on, of course, that Professor Mira focus on some part of this modeler part. But I'm talking about the especially focus on modeler part. So try to import our own data or try to import our own model, and also integrate or incorporate with this existing or equipped model. This is a kind of explanation of how we do. This is my topic. So and the K-Labo Japan, we have a study group of the K-Labo is a software platform, so that several universities in Japan will get together to do this kind of project. And then what we can do. So basically that in the K-Explorer or K-Modeler, previous speaker already mentioned many kind of data sources included in or connected with this this system, so that we can overlay many kind of model or many kind of output or result of existing model, so that overlay existing model, yes, existing maps, yes, and plus extract the information of interest with some condition. So also in the K-Explorer, we can extract putting or adding some special request to the computer. For example, to extract bigger than the 15-degree slope or distance from the 1 kilometer from this road or some kind of specific information, and also combination with other kind of modeling result. For example, soil erodible risk area within maybe more than 50 degree, and also the distance from the 1 kilometer or something. Such kind of web operation can be possible under the K-Explorer. And if you utilize the K-Modeler, we can do more. For example, overlay existing model with a map of ES estimation. For example, we can input our data on, for example, land classification data. In this system, we already have land use and land classification maps. But in some cases that we want to use our own data set. In this case, that we can also utilize in this system, input our own data and do the same, and do the estimation in this equipped ecosystem service maps or something. Also that we can incorporate our own model, and also that develop our new model and integrate this model into equipped model, or integrate that our model and also the other model or something. So such kind of thing can be possible if you utilize K-modeler part. And this is ARIES is global assessment and simple handling interfaces. K-Explorer and ARIES CI Explorer is a very simple, relatively easy handling interface. And data can be linked with a variety of open data sources, so that it already connected with many kind of data. For example, NDVI, NPP, or LAI, or carbon storage. This is modeling. Soil erosion, flood privation, recreation, some kind of these are equipped models. Also, we can import it into the many kind of models. Something like this. These are something like example. For example, one of this is ecosystem service model, carbon stock, air pollution model. Also, we are trying to do that renewable energy site selection model for the small hydropower, or geothermal, or wind power, biomass, etc. So that this kind of the K-model can be applied for many kind of environment and the sustainability application. In Japan, that we are doing several kind of the Japanese specific modeling by utilizing like a precise land classification map. Nowadays, we are using 10-meter grid land use map for estimating Japan modeling, and also renewable energy potential map for the small hydro or some other modeling. Also try to incorporate many kind of environmental data and also maps, and try to apply these kind of data into other environmental policy measures, something like EIA or something like that. Well, this is kind of ongoing project, not to finish everything, not to finish everything or all. So that this is one of the example. This is one of the area in the Aichi prefecture. It's elevation. And also this is one of the example of precipitation volume in the same area. And then we can, okay, this is like land cover type data equipped into the in this area system. And then we can utilize these kind of data, elevation or some other data, and we can estimate the groundwater volume. Something like this line is a river line, and we can estimate the amount of water flowing down in this river system. And then we can estimate that the amount of the electric power generation by utilizing small electric, small hydro power, electric power equipment. And then we can extract some kind of the disaster risk area, for example, soil erodible region or flood risk area, or some area is restricted to set up some equipment like a natural conservation area or some other thing, so that we can take it out, disaster risk area or environmental risk area, something like this. And also we can take it into consideration demand side. It's something like a population data, so that we can combine these kind of information to get into one, and then we can select the appropriate location for the kind of the small hydro. Something like this model is equipped like a test cases in our system. And then this is Japan model, and also we have already developing a global scale model. So this is like a schematic flow of this, like something like mini hydro potential, also social and environmental risk factor and demand factor, also some other energy sources data. Also, we also integrated into some other ecosystem service assessment into this system, and try to utilize it for the site selection model. This is one of the example. And also, this is the other example of the solar panel site. This is same concept, similar concept. And this is one of the examples of the solar panel already equipped in the Nagoya city. This red line shows like a panel existed into the already existed in the especially on the rooftop solar panel in the city center. And then we can check that like a soil erodible area. This map is available from the government, Japanese government. Also, flood risk area is also available from government. And also we can check that like land cover type information. And also we can check that height information from the, these are coming from the JAXA and NTT data and RESPEC. And also I will show some kind of the example in the just a moment in this okay, this is like one of the K modeler output image I have already calculated. This is Nagoya city. So this is one of the example of the crop production estimation model. Basically, this is based on the FAO, the A-crop model. It's a little bit modified. And this is also like a test data. So that like it's not the final one. The firstly, we can check that the land cover information and extract is just a vegetation site, especially agriculture vegetation site. And also we can input it into the evapotranspiration data. And also,
please share your screen.
Okay, I'm sorry. Okay, sorry for that. And this is land cover data extracted only for agriculture vegetation area. And then evapotranspiration data and coming from that global sources. And then LDVI is coming from global sources. And then okay, it's take a little bit time. And also that we can estimate that canopy coverage from the LDVI by utilizing estimated result from the this paper somewhere. This one, this paper. And then we can put some kind of parameter and get some tentative estimated result of the biomass. So such kind of thing is, this is just like an example. So that this is one of the crop model. Also, for example, also in the system, there is a carbon storage model. Also, we have tried to develop other kind of carbon model. Also, it's take a bit of time so that I think I can make it more large. This is our university, and for example, this is land map information. This is land cover type information. And this is a height information, and forest covers. This is like forest area. This is a forest area. And then, okay. This is a prototype of the carbon storage in a small area estimation, something like this. Also, we have several other models. So this is like a model, the K modeler, so that we can input it into our own data, and also that we can also include it many kind of new model, something like this. This is one of the, okay, this is a script of the crop model, something like this, so that we can make our own model, whatever you want. And I will go back to the slide. And then the last slide from me is thank you very much for your attention. And next, maybe Dr. Yamada will explain more about the small hydro model. Thank you very much.
So thank you very much, Professor Hayashi. Okay, so let's move on to the final presentations. So yes, so please get started, Yamazaki-sensei.
Hi, hello everyone. I'm Yuri Yamasaki from Tokyo University of Agriculture. As part of our ARIES training, so I'd like to introduce you to our small hydropower model. So I hope that you are now familiar with ARIES and KLove. So I will not demonstrate our small hydropower model, but I'd like to explain how KLove can help us to calculate small hydropower. So since the Great East Japan earthquake in 2011, so there have been three main types of new electricity supply expected in Japan. And the small hydropower system can meet these three challenges. So the technical uncertainty is small because the technology for small hydropower itself is largely well established. Also, in recent years, wind and solar power have been moving towards large-scale and centralized power generation systems, whereas small hydropower is more of a distributed power source because it generates a fixed amount of electricity. And also because it uses the energy of water, so it emits fewer greenhouse gases. And however, small hydropower has been slow to catch on in Japan compared to solar and wind power. So in particular, the rate of adoption of small hydropower is remarkably low, even though it has a greater power generation potential than in Germany, where adoption is more advanced. So one of the reasons for the lack of uptake of small hydropower is the inadequate estimation of potential at small sites of less than 1,000 kilowatt. And in this paper, they surveyed operators about the barriers and challenges to the widespread use of small hydropower. And the most frequently cited issues were obtaining permits and licenses, and project entity and planning. So small hydropower in Japan requires more licensing procedures than other renewable energy sources, such as community consent and water rights to obtain a license. And another reason is that it takes a long time to develop a project, as it requires a sequential plan from basic research to licensing and financing. So for these reasons, so it is important to develop and use small hydropower as a community-based energy source. So it is desirable that local governments, land improvement districts, like who are familiar with local conditions and have close ties to the local community, develop the project. So in addition, So community-driven development projects have not only introduced small hydropower, but have also been developed into town planning. But one question arises here. So if the local communities take the initiatives of introduction of small hydropower, so how can they estimate the power generation potential? So I explained earlier that one of the reasons for the slow uptake of small hydropower is the lack of potential estimation in Japan. So there have been some national surveys in Japan. However, it has been pointed out that these studies do not take into account the daily or monthly and annual variations in power output. And so therefore, do not match actual demand and supply. In addition, most of the examples of potential estimation at the basin or region level have been estimated using GIS. So GIS is essential for potential estimation. And so before we install the small hydropower model in KLab, we study the estimation method in GIS in advance. So here is the very simplest process of potential estimation by GIS. So there are 4 main steps in GIS. And here are the data used in each calculation process. So there's only the main data is shown. So there's actually a lot more local data used. So GIS requires users to collect this large amount of data by themselves. Without the data, you cannot analyze it. In addition, so whether the data is publicly available or you have your own collected data, so you need to change the format of the data to suit your analysis method. So, which is really complex operation. If you've ever used a GIS, you probably found that just adjusting the coordinate system of the data you're using can be a daunting task until you get used to it, or even after you do. Me too. So the next one is about GIS analysis tools. So it is necessary to use several analysis tools for each of the 4 calculation processes. So since many tools are used in the estimation of small hydro potential, even if the very easy, simple way. So here is only typical tools are shown here. And also for the GIS, about the GIS tools, so expertise is essential to select the right tool. And moreover, even after establishing these analysis methods, it is difficult to run them without errors, even for experts, because the default settings have to be changed when the target points or the data are changed. So I think GIS is really confused, complex, and difficult. But what happens when we use KLab for calculate the hydropower potential? So first of all, with K-Explorer, anyone can do the calculation easily on the web. So GIS requires a slightly higher specification computer, but with K-Explorer, you only need to open Google. In addition, so KLab does not need to import the local data, and the application autonomously acquires the public data and performs the analysis. For example, please imagine that you are planning to install a small hydropower system. If you want to install small hydropower in a certain area, but you haven't found a specific point yet, so you can use public data to estimate the rough potential, even if you don't have any survey data. In most cases, the resolution of the data used automatically by KLab is often very very large, like national level or global level. So the estimated potential is also very rough, but I think it can be used for just only make a rough idea of the range area. And the next step, so when you have narrowed down your choice of sites, you will have carried out a field survey. So we can use our survey data in the same way, same analysis we have done in step 1 to calculate the potential in more detail. So the great advantages of KLab is that the calculation can be carried out even without data and using local data. So far, I have explained the use of KLab in Japan, but it also has advantages for the analysis at the global level. For example, when we did the calculation in Japan, we used several Japanese data like these to specify the exclusion area, such as environmental protection area. However, it is often difficult to obtain such local data for international overseas surveys. So there is no significant difference in the calculation process between the Japanese version and the global version of the small hydropower model that we have developed. However, for the data, which is difficult to obtain, such as natural park area and landslide risk area, so we use the ecosystem service model, which is already introduced in KLab, and use the calculation results in our small hydropower model. So maybe it's already time, but I'm sorry. And also, you may have understood the advantage of using KLab to estimate the potential of small hydropower model. Moreover, I think that the use of KLab is effective for the new challenges the small hydropower is facing nowadays. So this is the report for 2019. So the small hydropower generation takes water from rivers. So there will be sections of reduced river flow, the river discharges. So it is feared that this reduction in flow will have a negative impact on the ecosystem. However, small hydropower is considered a sustainable energy source, so there are a few studies on the ecological impacts of small hydropower installations. Also, because the amount of water taken is directly related to the amount of power generated and the economics of small hydropower, so there is an incentive for operators to take as much water as possible. So in this paper, they reported that there is a need for further environmental impact assessments to promote the widespread use of small hydropower. So in previous estimations of small hydropower potential by GIS, the analysis was completed with a pre-installation potential estimation. I think it's of course, but in order to further promote the use of small hydropower in the future, so it is necessary to verify and simulate the negative effects on ecosystems and the positive effects on natural regeneration after the introduction of small hydropower. So in order to solve these new programs, KLab can be used to calculate the environmental impact assessment and the economic effects in the same application using like our simple small hydropower potential model and the ecosystem service models in KLab. So this is a very brief summary. So I have used a small hydropower as an example, but I think there are many other barriers or challenges or problems to local people, taking an active role in development in this way. So I expect that KLab can be used to solve kind of these various problems. So thank you at all.
Okay, thank you very much for your nice presentation. Okay, so now let's open the Q&A session. So if you have a question or comment, so please raise your hand by clicking on the raise hand button, or so please turn on your video camera. Are there any question or comment? Oh, so thank you very much. So please see the chat. So one question from Rivia. So could you please show step by step where to find the model which repository?
I can probably respond to this. It's very difficult in just 2 hours to give an idea of how the KLab ecosystem works. It doesn't really work like you have to find the models and the repositories. So every node can contain an arbitrary number of models, and they are typically synchronized from repositories using some kind of revision control systems like Git, for example, for those who know what that is. It's not, we don't have the time to explain what that is if you don't know, but it's a way to share source code online, basically, and you can connect those repositories to nodes. There isn't a fixed database of models. There isn't even a fixed database of data. And what the users normally do is never to look for models, but it's just to use concepts. And that's the entire purpose of the system. So you say what you want in conceptual terms. You want to know about carbon storage. Then you type carbon storage as your query, and the system will find what is the most at the moment, the most apt information to use in order to give you the response you want. So if you have access to the nodes and if you have access to the open source parts, you can use the modeler, and there is a directory in your machine, at least for the time being. It is not necessarily going to stay like that forever. Where some models are being written just to cache them, so you can have them and you can access them more quickly. That will be in your user directory. There will be a .klab/deploy directory, and you will find projects in there. You can open them in the modeler once you have it by just pointing to that in the file menu. So that's one way. But you will not get all the models, because there's no such thing as all the models. It's like wanting all the web. You have a browser and the web changes every minute. So it's not the same paradigm as loading models and using them. It's don't download the models. They are on the web, and at each moment that you use the system, it could be a different situation. If you have access to those models, you can also change them. You can customize them. But it's not the only way. Customizing model might mean to just make data available for a particular concept. Then the data will become candidates for choosing when you run the next model. And it may be a model written by someone else without access to those data, but the data will still be part of the choices that the machine can make. So it's a much more distributed system, and I hope I answered more or less how it works. So there are ways to do both things, find models and customize them, but it's not the main paradigm to use the system. The system is capable of finding the information wherever it is, and that's the main thing.
Thank you very much. How about
I was adding a link in the chat box about some documentation on how to import projects, for example. So you can follow up there.
Okay, thank you very much. So how about the second question? So I'd like to see how to input local database into KLab.
Yeah, I think it's more or less the same story. If you have data from a number of different possible sources, and we build adapters so that several different sources are possible and more will be available in the future. The most simple situation is where you can just create a project in your modeler and just drag and drop the data on the project. There is a folder called resources. You just drag and drop a file over that, and that will start the process of importing and parsing and validating all that information. Then you take it from there. What the system does at that point is build a resource, as we call it, a local resource, which is a URN that you can refer it to. And then you can publish the resource to a node if you want to, so that it becomes public for others to use, or you can just keep it there and use it for yourself. And I think we have some material online that actually can steer you through that process. I think Stefano will share the link. Stefano, do you want to take the other question about Invest and ARIES?
Yeah, I just noticed that I sent the link only to one person in the audience, so I need to copy the link for everybody. Yeah. So what was the question about him? I would like to ask in which scenario ARIES is more appropriate to employ rather than others. Yes. Oh, okay. I don't know how to answer this. I mean, more appropriate. In general, we are putting out a community effort. So we don't want to say that we have only a predefined set of models, but that we are building a web base of models, community driven, and I mean, it will be updated over time. You could think about like Wikipedia for modeling, so something like that. It's a completely different paradigm where there has nothing to do with a single application or a model set that is fixed and basically forces you to open the model and force your parameters, your input data in a certain way. We are thinking about it very differently. So it's a different philosophy and a different paradigm. So I wouldn't say it's more appropriate, but maybe it's more appropriate for the current technological developments that the world is undergoing.
Yeah, for example, to give you an example, ARIES is not an alternative to these other things. It can actually use these other things. For example, our forthcoming water model, the basic water supply model will be the Invest model. We have finished it. We are testing it now. I mean, it's not the Invest model, meaning that it's their own code. It's not. We have rewritten the code in a way that is more modular and can be, the modules can be swapped according to where you are, etc. But the base model will be the same water supply model that Invest does, because it's not a very good model, but it's a model that can actually run everywhere without major data requirements. So we have taken that approach. Our recreation model, as Stefano showed, is based on what the JRC in Europe had developed. So it's not that necessarily ARIES contains its own models and you have to choose between one or the other. Very often we take models that are common and we just incorporate so we can serve them in a much more efficient way. So that's basically the difference. We are a platform, we are not a set of models.
Okay, thank you very much. So how about the question from CARE? Using CARE model for customization, you can say something?
Yeah, well, I'm trying to read the question. Model can state and cover type, get further to place a real specific value. Okay, well, when you have a data source, so for example, a raster file that contains a particular observation, like carbon stored in the soil, stuff like that, that data source contains numbers. So those numbers need to be in a particular unit, and you have to write the unit. So the system will not let you annotate a data source without specifying the unit it's in. But then that data source can be used to automatically connect to a dependency for the same concept. And if you specify a different unit because you need it in a different unit for the model that you're running, then the conversion will be done automatically. So it is a way to just separate concerns. You take your data set, you annotate it perfectly, and then you put it away. You don't have to think about your data set anymore because your data set has become a strategy to observe the concepts it represents. The same goes for your model, and everything is completely interoperable.
Okay, thank you. So, Ferdinand, so one more question. So Robin Webera. So thank you to the presenters. So I have a question. So how does the system exactly choose the best available data source or model?
Yes, I'm happy to take this one because it's a crucial question, and it's also one of the most difficult parts when building a system like this. So we call the algorithm that chooses the match between a model and a concept, the resolution algorithm, which is the key algorithm KLab. And the same way that Google gives you uses their own page rank algorithm to basically decide which web pages to show to you when you make a query, when you actually do a search. That is the crucial algorithm. In fact, they keep it under lock and key very, very carefully. In our case, it's open. We use a number of criteria and they change all the time. But the main criteria, I think they are 13. We use both objective criteria that have to do with the match between your resolution, your context, the time you are in, etc. Those are fairly easy. So if you ask for elevation at 1 kilometer, you want a data set that is as close as possible to 1 kilometer resolution, but then there may be other, everything else being equal. But you can also use subjective indicators for data. Some of them come from the data providers originally. So if you know that your set is not very good, you can deprioritize it in a way that it only becomes used if you don't have anything better. But there are a number of criteria. There's very many of them. And also one mechanism that will be more important in the system as the usage of the system grows is the machine learning that can actually ensure that the data that are used haven't created anything controversial, including models that don't run or users that put in bad feedback or any other situation. So the machine basically is looking over every model that gets computed, and if anything strange happens, it memorizes that information. So in time, it can actually modulate and just fix the priorities so that the data that produce the best performance are always the best choice. But in general, it's a great question because it's a very complex point. It's actually maybe the most important part of the system, the one that makes the choice between data models for the concepts.
Okay, thank you very much, Ferdinand. So, are there any question or comment? I can accept. Nothing. Okay. So, may I have one question? So, please give us one more. Sorry. So, yeah. Future information once again about KLab development.
You mean where we're going? And there's so many things that are happening at the moment. One of the fields that we are evolving in much more into is helping governments, because that's where a lot of the demand is these days. It's not only natural capital accounting, it's also biodiversity, for example. So we are having conversations with the United Nations, the World Bank. We're discussing ways to promote this interoperability strategy. Maybe we can put the link to that as well. That basically is trying to pioneer the idea that all parts of government, international government, can be greatly helped by having information that can be readily connected. We do believe that making that happen is a game changer in terms of streamlining the capability of governments to make decisions. So that's one major area. That is an area that doesn't require very complex models, but it does require a lot of coordination and a very good, very stable infrastructure, and a lot of, so that is one of the areas. The other area that is important to me is using more detailed process and agent models for topics that actually need much more specific, much more science-driven decision, like migration, for example, and this kind of things. They're all based on the idea of building networks. So for me, ecosystem services, for example, are much more of a network issue. So I would love to map networks of providers, beneficiaries, being able to actually tell from which specific areas the benefits come and what happens exactly if you turn one area into another kind of land cover, etc., etc. So I want the system to become more specific and easier to use, even for models that are much more complex and much more detailed, because the system is fully capable of that. One thing that is coming over in the next months is water, for example. We're going to have fairly detailed water models that will do automatically the repartition into watersheds, river basins, doing all the hydrological calculations automatically in order to do water accounting, water prediction, potentially flood protection accounting, and all these kind of things. So you will see an evolution towards more and more complex models, a larger adoption, and potentially hopefully some adoption by big, larger international institutions, so that ARIES can become less visible as a brand name, but more important in terms of providing a substrate for governments to interoperate and work together.
Yeah, thank you very much, Ferdinand. And so thank you very much, Stefano, for sending a lot of file also linkage. Yeah, thank you very much.
岡田先生、ちょっとワンコメントいいですか？はい。Okay, so I want to add some comments. So I forgot to put some kind of data of my presentation. And also that we Japan, the K-Lab Japan is also sometimes organize some training also. And the BC3 also do some kind of training. In the last time that the ESP European Conference, they also hold like ESP ARIES training. Also that maybe 2019 also ESP Germany BC3 also holds like training also, so that we have a lot of time to do a kind of this kind of short training. But however, we want to find the time to hold some kind of training in some kind of academic conference, so that if you are interested to join this kind of training, we are welcome you to join this. So this is my comment.
Okay, thank you very much, Professor Hayashi. So are there any question or comment? I can accept only one question. Yes, yes, yes. Nothing. Nothing. Okay. So, okay, so, okay, so time is coming, so shall we close this training session? Is it okay? So finally, so I would like to thank both the speaker and the audience for providing such interesting session and discussion. So this session is now closed. So thank you very much for attending this training session. Okay, thank you very much.
Thank you.
Thank you very much.
Ferdinand.
Thank you, everyone.
Yep. Thank you, Stefano.